and also today, you have seen how to relate hydrodynamic quantities such as transport coefficients, such as viscosity, and retarded two-point functions of the appropriate components of the stress energy tensor correlation function. And I remind you that our goal was to calculate. So we had this relationship, and Guy also wrote it today, that if you have the retarded correlation function of the txy components of the stress energy tensor, provided our system is isotropic and momentum is along z direction. So then, in the low frequency limit, the expression for G retarded at zero spatial momentum, so we put here Q equal to 0. It starts, so it has a certain expression at low frequencies, which starts with equilibrium pressure, and then minus I shear viscosity times omega, plus terms which are higher order in omega, and also plus non-analytic terms, which I believe Guy will tell you about tomorrow, but they are higher order still than the first term in frequency. And this formula tells you that if you have some means to compute the left-hand side, maybe via kinetic theory or some perturbation theory or some other means, in a QFT of your interest, in QCD, for example, then all you have to do is to take this expression, expand this for small omega, and compare with the right-hand side. And then the first term in this expansion should be constant, and moreover, it must be equal to pressure, which you can also calculate by other means, independently from partition function. But the second term will be proportional to shear viscosity. And you can write down Kuba formula, sort of expressing eta exactly directly through G retarded. But this line is enough to read off viscosity if you know left-hand side. So what we're going to do today is to discuss a method which originated in string theory. And this method allows you to compute these correlation functions for any values of omega in Q in the limit of very strong coupling, in fact, infinitely strong coupling, and then you can compute 1 over coupling constant corrections. The advantage of this method is obvious. It allows you to actually do something in the completely non-perturbative domain for a gauge theory at finite temperature and other situations. The disadvantage is that it only applies, so this calculation that I'm going to describe applies for a specific class of quantum field theories for which we know that a dual description exists. Right? Not all theories are in this class, unfortunately. So if you come to me with your favorite Lagrangian or Hamiltonian and ask me to perform this operation and compute shear viscosity, for example, for a given quantum field theory, let's say for QCD, which is of most interest, then I would say, sorry, I don't have a dual description of this particular theory. I can only offer you a calculation for some other theories. And then I hope that maybe these calculations will shed some light on how viscosity behaves in systems like QCD. Okay, so that's important to remember. Okay, so let's proceed. And the title will be very ambitious: Gauge string duality. Now, before we start with discussion, let me just comment on terminology, because for people who don't work in this field, sometimes it looks a bit confusing. So several terms are used as synonyms. One of them is ADS-CFT duality or correspondence. And I will write this as a subset. I will use this symbol of gauge string duality, because this is what it is. And then maybe slightly loosely defined, but even more general, is the notion of holography. And then a particular limit of gauge string duality, which we are going to discuss today, is called gauge gravity duality. So gauge gravity duality is in some sense a subset of gauge string duality, and then ADS-CFT correspondence is a particular example, strictly speaking, of gauge string duality. But in the literature, these four terms are often used as synonyms, which is strictly speaking wrong. But people who know what we are doing, they don't bother to distinguish between them, but there is a distinction. Okay, just to warn you about this. Okay, so let's start with string theory. So I hope within 15 minutes. All right, so what is string theory? So string theory is a quantum theory of interacting one and higher dimensional objects. The main objects of interest are open strings, so we can have open strings. Then we can have closed strings. And then we can have these higher dimensional objects, which are often called branes. So you can think of them as hypersurfaces embedded in 10-dimensional space-time, because it will turn out the string theory for self-consistency must live in 10-dimensional space-time. And these hypersurfaces have a certain definition. I will talk about this a little bit later, but you can think of open strings sort of attached to these hypersurfaces, and in such a way that endpoints are free to move along the hypersurface of, let's say, p+1 dimension, but they cannot. The endpoints cannot leave this hypersurface. They are sort of attached, glued, and they only can move along the hypersurface, but not leave the surface. So these are called branes. And in some loose analogy, one can say that these are objects which are reminiscent of objects in quantum field theory. When you have a theory, for example, you write down some Lagrangian for lambda phi to the 4 theory, or some more sophisticated theory, and you start quantizing with Lagrangian. And if your theory is non-interacting, then you find quanta, you identify this quanta with particles. If your theory is weakly coupled, you still have this notion of these particles plus a little bit of interaction involved. When theory is strongly coupled, then it's rather difficult. So you can, in addition to these solutions of equations of motion, which you identify with particles, and usually if the system is non-interacting, it means that you have basically harmonic oscillator, right, in some generalized sense. So it's easy to write down the solution, plus some small corrections in interaction. But you can also have solutions to equations of motion which are non-perturbative. You can have solitons, you have instantons, and things like that, some monopoles and some topological defects and things like that. So in some loose analogy, the presence of branes in string theory is the presence of these solitonic-like objects, or topological defects, or these non-perturbative objects. Whereas closed strings and open strings, at least in the realm where we treat them perturbatively, they are analog of these elementary quanta which you have in the theory. Okay, the vibrations of these things will be elementary quanta. Okay, so this is the collection of the objects. Now you describe them as quantum entities, and for that you need the action, and one form of the action is the so-called Nambu-Goto action. Which is, so this is Nambu-Goto action, which is nothing but so you need to write down something which is invariant under all possible symmetries of your space-time, right? And if you have a closed string propagating in a space-time, then it swipes some surface, and what is written here is just the area of this surface. There's nothing else, right? So you can compare this with the action So compare this with the action for elementary particle of mass m, and you write down the same thing, except that elementary particle is a zero-dimensional object, so you integrate over the world line, and this is the only invariant you can write down, and you write down some coefficient which happens to be a mass of a particle to make the action dimensionless. Now, here is the same story, except that you have one dimension more, right? So your actually area will be not one-dimensional like here, it will be two-dimensional, and you write down the invariant expression for this area with a certain coefficient to make the action dimensionless, and this coefficient known is a tension of a string, and for historical reason it's written as 1 over 2 pi alpha prime, where alpha prime can also be written as the length of a string squared. And this is the only parameter of string theory. So one of the attractiveness of this string theory scheme is that everything else, including the standard model and all the number of generations and God knows what, must follow from the theory which has only one dimensional parameter, and all the rest is geometry. All the rest follows from geometry. All right. So this is this is the scheme. Now, for self-consistency, the theory must live in 10 dimensions. I will not comment on this further, but just say that there is a self-consistency. And then, of course, there is this question of how to get down to 4 dimensions to see what standard model and other fields which may be present in our universe. And this is a big open, actually, problem, right? How to compactify down to 4 dimensions. And it's a fantastic story which has taken about 50 years, actually, to unravel, and still is not fully understood. But we are not going to talk about this. We won't be needing any compactification of string theory, right? That won't be necessary. All we need to care about is self-consistency of this mathematical framework. So we will treat this as a self-consistent mathematical theory, and it will be enough for duality. So then the first thing you do is you find the spectrum of your theory, a spectrum of strings. And strings can be closed to open, so let's talk about closed strings. Now, the spectrum of closed strings, so what is it? So this is an object, this is some energy distributed in space, right? So it can vibrate as a quantum object. So you quantize it more or less like you quantize a typical classical string if you want to treat it as a quantum mechanical object. It's a little bit more involved when quantizing a harmonic oscillator, but not much, as long as a string is not interacting with other strings, right? So it's a free string propagating in flat space-time, and the spectrum is well known, and the spectrum consists of, so there is a tower of modes, infinite tower of modes. There are modes which are massless, and these modes will be of primary importance for us. And then there are massive modes with mass, which is not surprisingly inversely proportional to Ls. Okay. Now, massless modes can be classified pretty much like the states of harmonic oscillators, right? Which are very simple, just n, right? And that you can look at the spectrum. So here it's a little bit more involved. And you have to classify the massless fields appearing depending on what kind of boundary conditions you have on your fields in a string, because there are also fermions involved and so on and so forth. So the spectrum, the massless spectrum, involves these modes, right? So the fields involved in massless spectrum for closed strings involve the fields like G mu nu, then there is a scalar field, then there is a pseudoscalar field, then there is a two-form B mu nu, and then there is a 4-form with a certain additional condition, which I won't specify. And then there are fermions, and fermions come in, so there are different, okay, let me just put like this. So there are different types of fermions. We don't really need to specify what they are. So this spectrum contains the symmetric field G mu nu, which will be identified with a graviton. So in some sense, the spectrum of closed strings for free, the low energy approximation to string theory, closed string theory, gives you gravity plus some other fields. So this happens actually to be a supergravity which was known in the 80s before this thing was understood as string theory. And one can write down equations of motion for these fields. Right, so how can you do it? So at low energies, and low energy always means that energy is much less than the scale set by Ls, 1 over Ls. So equations of motion can be derived for massless modes, can be derived. They can be derived also from self-consistency of the theory, which I don't have time to discuss in any detail. But the equations look very suggestive. So these are equations in 10 dimensions. And the equations are, I will write just one of them only partially. R mu nu is equal to 1/2 d mu phi d nu phi plus some other fields plus very interesting field which comes from this 4 form. So this is like a generalization of Maxwell field, right? In Maxwell case, you would have A mu, but here you have a form with 4 indices, right? So the field strength of this form will have 5 indices, and this is the famous F5, which I'm writing, lambda rho sigma kappa, and then F nu lambda rho sigma kappa upstairs, right? And okay, just to be completely pedantic, so there is some redefinition of this field. And then other other equations. So there is a long set of these equations which couple together all these fields. So these are partial differential equations, nonlinear, horrific system, and these are only massless modes. Okay. So when we talk about string theory at low energy, closed string theory at low energy, we always refer to this system of equations. And one of the appeals of string theory is that sometimes people say, well, string theory actually post-dicted gravity, right? In some sense, it predicts gravity. That the low energy limit of string theory gives you Einstein's equations of motion, effectively. Right? R mu nu equal to some other stuff, some other fields which propagate. Right? So you recover what you already knew. You recover Einstein's equations of motion for general relativity in 10 dimensions. Fine. So one other remark is the following. So we have here, so we can now forget for a moment about strings and just say, well, what we have is 10-dimensional gravitational theory with Einstein's equations. And on the right-hand side, there are some other fields. Now, this field F is reminiscent, it's some generalization of Maxwell field. So if I had here F mu nu instead of these 5 indices, I would say, well, I have some, and forget about the scalar for a second, right? So I would say, well, there is gravity, and then the T mu nu on the right-hand side contains some Maxwell field, right? So such equations can have solutions, right? In ordinary general relativity, they can have solutions in the form of the Reissner-Nordstrom black holes, right? So you have black holes which are charged. They're charged under a Maxwell field, right, which is sitting on the right-hand side of the equations. So similar things happen here. You can have solutions to these equations of motion, exact solutions, which describe a certain generalization of a black hole, but now in 10 dimensions. And this black hole will be charged under this field, F5, right, or C4. Okay? So this is one of the charges which emerges naturally in string theory, and it's called the Ramon-Ramon charge for historical reasons. Okay? But again, so morally speaking, this is not different from Reissner-Nordstrom in ordinary general relativity. So let me write this solution. So solution to this, one of the solutions, has this interesting form. I will write the metric. ds squared, 10-dimensional, is equal to h to power minus 1/2 of r. And here I have f with minus sign dt squared plus dx squared plus dy squared plus dz squared. And then bracket closed. And then I have plus h to power 1/2 as a function of r, dr squared over f plus r squared d omega 5 squared. And here h will be a function 1 plus L to the fourth divided by R to the fourth. And little f is 1 minus R naught to the fourth divided by R to the fourth. So let's stare for a moment at this. This is exact solution of the equations of motion at low energy, okay, string theory. So what this solution actually describes, it's a 10-dimensional metric. So inside there is this d omega squared 5. This is a metric of a 5 sphere. So this is a metric of a 5 sphere. If you forget for a second about this 5 sphere, the rest is interesting, right? So this function h has this interesting form. Then r is going to infinity. When r is very large, h goes to 1, right? So h goes to 1, and also f goes to 1 if r is very large. So if you take r to infinity in this metric, this goes to 1, f goes to 1, right? This h also goes to 1, and this f goes to 1. So what you recover here is minus dt squared plus dx squared dy squared dz squared, which is Minkowski metric, flat Minkowski metric in 3+1 dimensions, plus dr squared plus r squared d omega 5 squared. But this is nothing but a flat Minkowski metric in 5 dimensions written in spherical coordinates, right? dr squared plus r squared d 5 squared, right? So the moral of the story is that at very large r, at far at infinity, this metric just describes 10-dimensional Minkowski space, nothing else. Okay, it is asymptotically flat. But somewhere in the middle, it describes something interesting. It has a horizon, so this function f goes to 0, it's at value r equal to r naught, and also some other properties which I won't go into. But it has this horizon, has this Poincare. I mean, if I if I put r naught to 0 for a second, it has Poincare symmetry. So there is a kind of, if you want to draw this solution, then you will get some picture in which you have a translational invariant horizon. Again, if you put f to 1, right? So you have some solution in which you have this Poincare invariance, right? And then there is some curvature. There is some curvature involved, and the solution goes to flat Minkowski space far at infinity. Okay. So fine. So okay. So we found some solution. We also can relate these parameters. So you have this metric has 2 parameters. One of them is capital L, and one is R naught. And you can calculate the Hawking temperature of this metric. I will not do it on a blackboard, but R naught is related to Hawking temperature of this metric, and L, capital L, is related to the mass of the object, or which happens to be the same, the charge. Because remember, this is solution similar to Reissner-Nordstrom. It is charged under this phi form, and therefore there is some charge involved. And you can relate charge and mass with some relation, so in some sense it's the same. And so these parameters, one of them describes the Ramon-Ramon charge, and the second one is related to the temperature. Fine. So this is a solution of low energy, specific low energy closed string theory, specific type of closed string theory. Fine. Well, now let's look at open string spectrum. Now, open strings can also be quantized in a similar manner. So we have open string spectrum. And it's more or less the same. So again, you have some massless fields, and then a tower of massive states. So these are massive states whose masses are inversely proportional to string length. But then there are massless modes. And these massless modes again can be classified, and these massless modes contain a mu, and then there are some scalar fields, and then there are some fermions. I'll put some indices, and so I will go from 1 to 6. There are some scalars, and then alpha is 1 or 2, and then A is 1, and so on, 4. So what are these? So these are low energy modes, and just like there, right, there is a solution. There are equations of motion. There is a solution. So here you can also write down either equations of motion, or you can write down the action, which is more or less the same. And the action for these massless modes will have the form. So I will write down the Lagrangian. Lagrangian has the following form: 1 over g squared Young-Mills, because you recover. So these are gauge fields, mu gauge fields. Trace, and here I have 1/4 of f mu nu squared, and then some other fields which are scalars with covariant derivatives acting on them, I d mu phi I summation over I, and then these scalars happen to be, so there is so these are matrices, and they happen to be the potential term involves a commutator squared of these guys plus fermions, which I'm not going to write. Fermions plus corrections. Of course, this is all low energy, right? So you have corrections because at higher energies there are different massive fields which enter the game, but we ignore them because we want to stay at low energy. Okay, so this is a gauge theory plus some other fields. So it's not a pure glue, right? There are some fermions around, there are some scalars around, but it is a gauge theory for which we can write down the Lagrangian. And now remember this picture of the brain, right? Of the brain which I was showing in the very beginning, and the brains. So the brains are classified also. And there is a class of brains which are known as D-brains. D-brains. And D-brains, D stands for Dirichlet boundary condition. And the Dirichlet boundary condition was that the open strings can end, in fact they do end, on these brains. So it could be like this. And these endpoints are free to propagate. So for example, if I consider D-free brain, then the world volume of this brain is 3 + 1 dimensional. And these endpoints are free to propagate along this world volume. Okay? So these are also solutions of equations of motion of string theory. Now, what does it mean? I mean, this picture, so and the brain and so on, right? So 3 + 1 dimension is pretty much like our 3 + 1 dimension which we see around us. So in some sense, we can imagine ourselves being part of the brain, right? So suppose all of 3 + 1 dimensional world around us is the surface or a world volume of a 3 + 1 dimensional brain, right? How do we know? It could be. Then, according to this definition, there are open strings which stretch all the way into 10-dimensional space. But of course, we don't perceive 10-dimensional space. We can only see endpoints of those open strings. But the endpoints are free to move throughout the world volume, 3 + 1 dimensional, right? How do we know they stretch somewhere in extra dimension unless we do some experiments, and so on, right? And of course, these open strings are quantum vibrating objects. So we perceive, how do we see the endpoint of a string? How do we perceive the endpoint of a string? We perceive the endpoint of a string because of the quantum vibrations of this endpoint. And at low energies, these quantum vibrations are described by a gauge theory of particular type. So this means that if you see, for example, an electron floating around, this well may be an endpoint of an open string stretching in 10-dimensional space. Right? There are no fundamental fermions in this particular Lagrangian. This is just an analogy, right? But quanta at low energy, right? We can do only experiments at sufficiently low energies, not Planck scale, right? So we don't see all the tail of this Lagrangian, but we see only massless, only the lowest energy modes, and they're all around us. It's not that there is 3 or 4 strings attached. Every single point of this 3 + 1 dimensional brain is defined as an endpoint of some string, right? So it's a continuum, if you want, right? So there is nothing there on the surface, on the world volume of the brain, except the endpoints of open strings. Okay, they define the locus of these strings. They define the brain. That's the definition, if you want. Okay, so this is the object we want to describe. So if you want to describe dynamics of this brane, you have a Lagrangian, and you can write down equations of motion and things like that. Now, we will be interested in a collection of these branes. So you can take one, but you can also take more together, like sheets of paper, folded like this. And I would like to consider NC of these branes, D3 branes. So you can actually calculate the force between the two branes, and at 0 temperature, this force is exactly equal to 0. So you can put them on top of each other as many as you want. They don't repel each other, don't attract each other. And so, okay. So this is the thing I want to consider. If I have NC branes, it turns out that Lagrangian here is actually the gauge theory with a gauge group SU NC. And coupling constant G Young-Mills. And it will be useful to introduce a 't Hooft coupling, which is G squared Young-Mills NC, because you already may suspect what is going to happen. I will take my NC to infinity. I will consider a large NC limit of my system. And then the useful variable will be 't Hooft coupling lambda rather than G squared Young-Mills. Yep.
So there are like two branes, one end point of the string is here and then another one
Yes.
is here.
Yes.
So when you have NC of them, does it mean that sometimes these strings pass the branes and then like, you know?
No, so the system which so you can have these branes separately in space, right. And then this is exactly how you describe, right? So there is one endpoint here and one endpoint on this string. But I want to consider a situation in which all NC branes are together, completely squeezed at one point, so they're infinitely thin, all of them, right? So then this situation, so you have one open string N here, and another open string on the other sheet, right? But when I bring them together, the second end, right? It is glued to this whole object, right? So it's becoming this, right? And actually, it has an interesting description in terms of some massive modes becoming massless and so on. So that's all right. Yep.
I have a question about the dimension. So is this dimension 10 consistency condition independent of the gauge group that you use?
Yes, dimension 10 is a consistency condition for the whole string theory.
Like any gauge group?
The gauge group only appears in this particular construction, this particular solution, right? The gauge group knows nothing about d equals 10 at all. Okay, so this is not. They are not. These are different beasts, right? So to speak, right? I mean, the fact that string theory must be formulated in 10 dimensions was established long ago before people realized that there are brane solutions in the theory. So these are independent things.
But some consideration like anomaly or whatever don't they depend on the gauge group?
Yeah, but it doesn't affect the main thing that the whole theory is formulated in d equals 10, right? And then if you have a specific solution, for example, you have some intersection, because these branes can come in various forms, right? It could be intersection of these branes and God knows what. Right, so of course then you have to think about anomalies and consistencies of these low energy description and so. So then yes, you may think about what kind of groups are allowed and things like that, and what they are doing. But this does not affect the main thing, that the whole story is embedded in 10-dimensional space-time. Right. So that yes.
Are we considering a situation? So we have these NC branes which are all so overlapping.
Yeah.
And then we have the strings. Do we consider situations where the string is affixed to one brane at one end and then another brane at the other end? Or do we consider situations where the string is just affixed to one brane on the one end and then the other end is free floating?
No. They're always, so this picture perhaps is a little bit deceiving. So there is another brane somewhere. So the open strings are not floating around in space, right? They must be attached to somewhere, right? So that, yeah.
So that Lagrangian is Lagrangian for a 10D theory or for a 4D theory?
No, this is 4D. So this Lagrangian is 3 + 1 dimensions, because this is. As I said, right, so what is the brane, right? What is the brane? The brane is that at low energy. There is nothing else, right? It's a definition if you want, right? So these are fields. So imagine this room is a brane, right? So then at each point in this room, there is some microscopic structure, right? And you can quark, right? And you can think of this microscopic structure as being an endpoint of a string stretching in 10 dimensions, right? But for you, the Lagrangian that you're writing about your 3 + 1 dimensional world will be this, nothing else, right? Okay, so let's proceed. So what we have is the open string picture. So open string picture of the collection of NC D3 branes. But we also obtained a closed string solution whose horizon has an interesting property of being 3 + 1 dimensional, right? And so we have some multi-dimensional object which kind of looks like a brane, right? At least it has this symmetry, but it is yeah. So it looks more or less like this. So let's call it a closed string picture. And all of this is embedded in 10-dimensional space. And then you suspect that perhaps this solution, gravitational solution there, is actually describing this collection NC of NC NC D3 branes, right? So why would you say this? You would say this because ultimately remember that each brane, each string and each brane has some tension, which means mass per unit world volume. And this means that if you take a large collection of them, they will start curving space-time like any other object, right? So if you take many of these branes, it's not inconceivable that they will produce some gravitation, they will curve the 10-dimensional space-time. And perhaps in some limit, this collection will look like a gravitational solution with a non-zero curvature and so on and so forth, right? So it's not inconceivable that a symmetries match, you can match them carefully, the symmetries match. So it seems like maybe, another thing which I forgot to mention is that this object, this gravitational solution, is charged under Ramon-Ramon field, and you can show in string theory that this collection of branes is also charged under the same field. So you kind of see that you have two pictures which apparently describe something similar or something identical. All right. So how do you check? Is it the same object? How do you check in general? So how do you recognize? So for example, you have two objects, a bottle and a glass. How do you know they're different? Well, you know they're different because you do scattering experiment with your eyes, right? But this is a scattering experiment, right? You have quanta of photons, they come in there, right? They scatter, they come to detector, right? And you make a conclusion, right? So exactly the same you're going to do here. And people did this in 1996, 1997. It was actually very, very popular activity at the time. So they did scattering experiments with branes. So you take some field, it could be scalar field or a graviton, for example, and you scatter off object to the left and object to the right and see if the result is the same, right? That's how you compare. And it turned out that, so do scattering experiments. So do experiments with branes and compare it to picture. So for example, so you can scatter the graviton or scalar or some other fields and compare the results, right? So with branes in open string picture and independently closed string picture. And compare. Okay, so this has been done, and let me just recommend you one paper which I particularly like. It's a paper by Igor Klebanov, who later will lecture in the school. It's a beautiful calculation, very simple technically, well, relatively simple technically. And for anyone who is interested in holography, DSFT correspondence, this is a must read. I mean, this is a very short calculation with comparison of open and closed strings and with scattering of a scalar or graviton. And what Klebanov and others showed was the following. So if you do the scattering, so typically you write down your equation of motion for your, for example, you send some field. So for example, you send the graviton here. It's scattering of some wave of black hole. You know how to compute this. I mean, people knew this for decades. And here you send the same graviton from infinity, h mu, right? This h mu, so this is the energy wave. It couples to the energy momentum tensor t mu of the brane, and of the brane means energy momentum tensor coming from this Lagrangian. And you know how to write down the coupling, so they couple like this, and therefore you can calculate the scattering amplitude sigma as a function omega here and here. And this is what Igor and others have achieved. Now, typically in these calculations, you have the following. You have some sort of the effective potential. So the equation of motion to solve is basically a box times phi, box in curved space-time, phi equal to 0. You can rewrite this equation, as often is done in scattering experiments, as a Schrödinger equation with some effective potential. I mean, any second-order linear ODE you can write down in this form, so this is not very difficult, and you can analyze this potential. And it turned out that the potential had the following interesting form. So there is some region which is called near horizon region, and then there is a sharp maximum, and then the potential goes essentially flat. So we have 10-dimensional Minkowski space, and the height of this potential depends on the energy. So this is low energy peak. Let's say low energy, it means that the peak is high. Okay. So and then there is some near horizon region of your metric. And here, so this is a closed string picture which sort of separated at low energy into two regions. One of them is flat 10-dimensional Minkowski space, and the second is near horizon region of the metric which I was writing on board. All right. Now, if you look at the the metric again, right? I don't want to write it on board again. But if you look at it and do a small exercise, so near horizon region, remember we had this function h, right? H, which was 1 plus L to the 4th, R to the 4th, okay? And we said that then R is extremely large, then H goes to 1, and we go to flat Minkowski space. Now we take the opposite limit, the near horizon limit, then this object, this second term, is very large, and you can neglect 1 in comparison to this. And then if you remember, there was also the power of 1/4 or 1/2, sorry, plus or minus sign sitting in the metric. So you take the square root of this or the minus square root of this. Okay. So do this little exercise and convince yourself that in the near horizon limit, the metric of the brane which I wrote goes into a very simple form. Namely, it becomes metric of 5-dimensional anti-de Sitter space times the 5 sphere. Okay. But now, fine, so we have this. But in the open string picture, you have Yang-Mills theory of particular type. So in this picture, you have Yang-Mills theory in 3+1 dimensions, and flat Minkowski space, and Minkowski space 10D. All right. So Yang-Mills theory at low energy is the brane itself, and then there is 10-dimensional Minkowski space. And here this scattering experiment tell you that, okay, so there is 10-dimensional Minkowski space, and this ADS5 crosses 5 region, and some excitations which propagate in this geometry. And the most important thing was that when you compute sigma, the cross-section of the scattering, in this picture and in this picture, the result was the same. That was the result of Klebanov and others. And therefore, you suspect that if you take the low energy limit, then you can identify your Young-Mills theory with this Lagrangian and so on, with the near horizon region of this geometry, which happens to be ADS5 crosses 5. Right? So, well, it still maybe it doesn't look very obvious, and I must say that so this ADS-50 correspondence, which I'm talking about, engaged string duality in general, remains a conjecture. It's not proven, right? So obviously there is no way I can, give you some convincing proof of, right? So all these arguments are heuristic arguments, but this conjecture survived many checks, and so people sort of believe that, well, of course, any sophisticated check which appears tomorrow and fails would be enough to falsify the whole thing, right? But so far, nobody managed to produce such a failing test. So how about, so is it plausible in general, right? So this Young-Mills theory, this particular theory in 3+1 dimensions, has a very interesting property. This theory is superconformal. Superconformal. So it has many symmetries. And in particular, it means, so superconformal means that the beta function of this theory is exactly equal to 0, so the coupling actually doesn't run. This is just this particular example. There are many other examples of duality, but where this does not hold. But for this particular example, this is true. And the conformal symmetry in 3+1 dimension is corresponds to the symmetry group SO42. And in addition to this group, because the symmetry is not only conformal but also supersymmetric, it has fermions and the number of degrees of freedom matches, and it has 4 supersymmetries, and 4 supersymmetries have a specific symmetry group which is called R symmetry, and this group is SU4. And if you look on the left-hand side, you look at the isometries of your geometry here. Now, the isometry group of ADS5 is exactly SO4, 2. And the isometry group of a sphere is SO6, whose algebra, SO6 little, is exactly the same as algebra SU4. And we only need algebras to match. So the symmetries match on left-hand side and right-hand side. Now, one has to work a little bit harder to match other parameters. Remember that here in the geometrical part, we had our solution in closed string theory, and this solution had this parameter L, which was related to mass of the Ramon-Ramon charge of the brane. And we also have L string right on this side. Now, one thing which I didn't tell you is that string theory has another parameter, but parameter in quotes, so let's call it GS. So this is a string interaction parameter, the coupling, string coupling. So suppose you have 2 closed strings, they can merge, they can disentangle again, and you can have string loops and things like that. Now, GS is not a true parameter in the sense that it is an exponential of the expectation value of one of the fields in the string spectrum, the dilaton. So in this sense, LS, what I said before, was true, right? The LS string length is the only fundamental parameter in the theory, but it's convenient to treat this as another parameter in string theory, although this is not a fundamental parameter. So these are parameters of the sort of geometrical side, right, this gravitational side. Now, how about the Young-Mills parameters? What we already have them, right? So we had a coupling, we introduced coupling and Hopf coupling, so the group is so the number of colors, and then we introduce it Hopf coupling out of this NC and G Young-Mills. So one can match these parameters, and I will write down this as an equation which involves all of them. So this is Hopf coupling lambda, and then GS is identified with G squared Young-Mills over 4 pi, depending on how you normalize the generators. But the moral of the story is that the two sides are related. The string geometrical side and the Young-Mills side are related by these equations. I will not say anything about how they derived. It's not terribly difficult. So one thing is more or less obvious, right? So you have NC d branes, each of which has a certain tension, right? So NC times the tension of each brane, right, is the total mass or mass density of this whole system, and it must be matched to the mass of this gravitational solution, right? This is how this equation can be derived, right? And in similar fashion, you can derive this as well. Great. Well, not quite, but so now, so there was this conjecture that the right-hand side, so the description, so again, so philosophically what we are doing, right? We have some solitonic-like object in a theory, and we can describe this object in two languages. One is the language of open strings, that means Lagrangian, and the second language is the gravitational solution of closed string theory. But we are describing one and the same object. It's conceivable that we are describing, it's like we are describing the same thing in say, in English and in Chinese, right? And then you can think, well, maybe we can just build a dictionary between two descriptions, right? So that's if it is the same object, right? So then, then this is this will become a dual description. Fine. So how this dual description actually works in practice, right? So far, it was more or less a philosophy plus a little bit of formulas. But of course, we are talking about quantitative description. And as I described last time, we can think about the duality in general as a change of variables in our path integral, in our partition function, for example. And this means that if I have a Young-Mills theory in 3+1 dimensions, I have a generating functional for my correlation functions. And I remind you that our goal is to compute G-retarded for txy, right? So this is the whole thing is just to do that, right? So Z is supposed to be just like in Kramer-Swanier duality, in a sense, right? It can be written via different variables. And these different variables of degrees of freedom, they involve particular type of string theory, which is known as type 2b. So I didn't say this, but there is a certain type depending on boundary conditions. The one I described was the type 2b string theory, not type 2a. String theory on ADS5 cross S5. And the statement is that these two partition functions, these two z's, are equal to each other. So there is an identity. So these theories are identical as quantum theories, right? So in other words, there is a change of variables. We cannot make it explicitly. We don't know how to, unlike Kramer-Swanier duality, where I can actually explicitly rewrite this in terms of this. We don't know how to do it. That's why, that's why it remains a conjecture, right? And I will put a little question mark here to remind you about this. But the statement is that left-hand side and right-hand side are identical as quantum theories. And so this was Maldacena, November 1997. Now, well, this is fantastic, except that if you look at type 2b string theory on curved space-time, such as this one, we don't really know very much about it, even perturbatively. So it's a very complicated object to treat. In flat space, fine, but in curved space-time, it becomes. So in other words, we don't really know how to calculate the right-hand side for arbitrary values of parameters involved in these theories. But we can take a certain limit, right? We can take a certain limit, and let me take the limit here. Instead of a full string theory, I will describe a limit in which this parameter capital L with respect to Planck length will be very large. So let me say going to infinity, for example. And then the other parameter, the same parameter L on the string side, the same L is here, relative to string length, its dimensionless parameter, is also going to infinity. And if you take this limit, then, so this limit means that you neglect the complicated string geometry, this limit, and this limit means that you neglect quantum gravity loops, which you still don't know how to calculate anyway. So if you take these two limits, out of this z, what survives is e to the I, e to the minus s gravitational, which depends on this j tilde, plus some corrections. So in some sense, again, philosophically, you can think of this as a saddle point approximation for your path integral. So you only consider, in this limit, you only consider the dominant contributions, and these dominant contributions are classical gravity solutions. So classical gravity dominates in this limit. Okay? So then out of the whole z, out of the whole integral, only e to the minus s classical gravity survives. And this is much better because we know everything about this object. We know how to calculate everything here. But if this is a duality, then on this side, you must have also the same limit, right? And remember this relationship between those parameters. On this side, L over L Planck will correspond to taking the limit of MC going to infinity, right? And this limit, L over Ls going to infinity, corresponds to taking the 't Hooft coupling to infinity. And otherwise, nothing changes. So this is still Z Young-Mills of J, right? And this is still supposed to be equal to this, but now it's Z Young-Mills in the limit in NC going to infinity and lambda going to infinity limit. Okay? Fine. So what we achieved by taking this limit is some operational space, operational freedom. Because we know how to calculate things with classical gravity, even in 10 dimensions, who cares? We know everything about this right-hand side. But look at the left-hand side. Left-hand side is a generating functional of Green's functions and free energy and God knows what you want to calculate. In the limit, infinite colors, that's fine, infinite coupling. So by this line, we have access in particular to Green's functions that we want to calculate for viscosity and so on, in the limit of strongly coupled theory. So this is a gauge theory of particular type in the limit of infinite coupling. And you can calculate whatever you want, right? The time-dependent correlation functions or non-equilibrium behavior, everything you, from classical gravity where you know everything how to calculate, okay? So this limit is called gauge gravity duality. So this is gauge string duality. This is gauge string. And this is gauge gravity duality. And not surprisingly, this generated a lot of interest because, of course, people gained access to the non-perturbative domain. And of course, you have to develop, so it's not enough just to write down this equation like this. You have to develop the dictionary. You have to actually explain how to compute particular objects of interest, such as Wilson loops and correlators and so on. And this is the thing that we are going to do in the next half an hour. So let me pause maybe for a very short time and ask if there are urgent, let's say, questions, because now I want to do the calculation, right? So this is, yeah, please.
Maybe I missed it, but the LP parameter, what is it again?
This is Planck length. This is Planck length. So okay, so this is, yeah, it's, okay, let me talk about. So when we consider strings, right, so I said that there is this parameter ls, right, which is fundamental parameter of strings, or alpha prime or ls squared. So it tells us, so what's the ratio of L to Ls means? It means that how far you are from a point-like particle. So from far away, you can consider your strings as a point-like object, right? So with stringy geometry, of course, it could be very intricate if you come very close, right? This vibrating thing could be extremely right. So this ratio, the ratio of L to Ls, regulates how far you are from a point-like geometry, right? So this is a stringy geometry in the sense. And then you can also ask, what about classical geometry? So here you just think of string as a classical object, right? That could be and geometry of a classical object. But of course, you can also have quantum loops. So in particular, you have graviton loops, right? Even in classical theory, you have quantum gravity, for example, right? But in stringy case, so there is also this situation in which you have to treat also quantum corrections to your classical geometry. And quantum corrections related to quantum gravity are governed by L Planck, right? So there is another parameter of goodness of the solution, so to speak, right? So you can think in the following terms. So suppose somebody writes a metric, for example, Schwarzschild black hole metric, right? This metric in string theory will receive corrections. What kind of corrections? It will receive corrections due to the fact that strings are not point-like objects, right? So these are geometrical corrections, so to speak. And on top of that, it will receive, or together with this, it will receive corrections because you have quantum gravity loops. Okay? So you have to, when you say whether or not your geometry is good or whether or not you're going to classical gravity geometry, you have to treat both of these parameters, right? So if these parameters become very small, right, then you're back to point-like object, meaning normal fields, right, in our time, without any loops, without any quantum corrections, which is classical gravity. Okay, so that's this limit. Other questions? Yeah.
So if I understand correctly, we still don't know whether there's equality between the Z, Ym, and
yes.
So how do you find the J tilt?
Yeah. We'll try to do it now, actually. So I will. Okay. So you see again. So it is a conjecture. So in a sense, within a conjecture, it is known how to equate this to this. The question mark here simply refers to the fact that we cannot prove this mathematically rigorously. So we cannot, like in Kramer-Svanier, you can actually starting from this, you arrive to this. Nobody was able to do it for ADS CFT. So you conjecture that this object is equal to this object. You set out the rules. You write down the rules how precisely this J tilde related to J and so on. So this is all known. And then you do calculations and you check. In some situations, you can predict, without doing any calculations in string theory, you can predict that, for example, in Young-Mills theory, at any coupling, the particular, for example, scaling dimension will not change with coupling at all, right? And then you do a gravity calculation on this side, and you check whether this is the case, right? We can compute anything perturbatively here, right? And if they don't change when coupling changes from 0 to infinity, then it is a prediction for the gravity side, right? You do the gravity calculation, you must obtain the same quantity as it was in the perturbative quantum field theory at 0 coupling. So this type of checks has been done extensively at the end of 1990s and 2000s and so on. Okay, so okay, so let's do the calculation. Let's do the calculation. In order to do the calculation, I will rewrite this near horizon metric in the following form. Remember, we had this metric in 10 dimensions, and this metric was split into 5-dimensional part, and then there is a d omega squared 5 with radius L squared. So I will forget about the 5 sphere because this is part which describes this internal symmetries of supersymmetric Young-Mills. So let's not bother with this. And I will only focus on this 5-dimensional piece. And the 5-dimensional piece I will write in the following form. So I will introduce Hawking temperature of the solution. And the new coordinate u, which will be r0 squared divided by r squared. And I do the change of variables. Just it is more convenient for me to use these variables, but otherwise the metric will be the same. And the 5-dimensional part, 4, 5, u squared, du squared. So this is our this is anti-de Sitter, asymptotically anti-de Sitter Schwarzschild black hole. It would be at 0 temperature, it would be just ADS 5, but I'm working at finite temperature, so this is ADS Schwarzschild black hole in 5 dimensions. Fine. So little f here is 1 minus u squared. And this solution is describing, so this solution of low energy equations of motion is the thermal state of our Young-Mills quantum field theory at some temperature T. In the limit, of course, in NC going to infinity, lambda going to infinity limit, of course. All right. Okay. So this state has an entropy. So let's compute the entropy. First result. Now we compute the entropy density, right? Because this brain has infinite extent, right? So the total entropy is infinite, right? But we can divide by free volume, and then the total entropy divided by free volume. This is entropy density. So how to compute the entropy density if you have a gravitational solution with a horizon? Wittgenstein and Hawking told us in the 70s that the entropy of such a solution is equal to 1/4 in Planck units of the horizon area. So it's trivial in some sense, by looking at this solution, to write down the expression for the entropy as 1/4 of the area of the horizon. All right, and you can do this, and this gives you a first holographic result. So entropy density, remember that whatever you compute, the entropy of this state is supposed to be the entropy of Young-Mills theory at infinite coupling and infinite NC. Okay, so let's see what we get as the area of the horizon. So this is S at lambda. Let me put S at lambda going to infinity, and the result of this calculation is the following: pi squared over 2 n squared c t cube. All right. So here I used this relationship between parameters like NC, lambda, and so on two sides to replace the appropriate coupling. So now it looks like the entropy in a gauge theory, right? It must be T cube, right, for bidimensional analysis. But the interesting thing is there is this coefficient. Let's compare this coefficient. Of course, we can also compute the entropy in the same Young-Mills theory, just like we did for ideal gas of quarks and gluons, right? We just write down the Stefan-Boltzmann law and count the number of degrees of freedom, right? So we have a gluon here, right? We have fermions, we have scalars, and so on. And you can combine all this number of these degrees of freedom in a prefactor of T cube and write down the answer. So this is a really trivial calculation. Equally trivial as computing the area of a horizon. But that calculation was the ideal gas calculation, right? And here is the opposite limit at S going to, at lambda going to infinity. So if you do this calculation, then you discover that this answer is actually 3/4 of the S, the entropy density at the opposite end, at the ideal gas result. All right? So this is the first result of holography. You take the gas, or you take a theory, Lagrangian. You can do any perturbative calculation in this theory you want. In particular, you can compute the entropy of the ideal gas, switching off all interactions. The entropy is given by some expression. Then you ask a question, how the entropy changes with coupling. Now I turn on some coupling. In principle, you can do the finite temperature perturbation theory, as Guy described in his previous lectures. With some pain, you can calculate corrections to this ideal gas result. These corrections will go as non-perturbative powers of lambda and so on and so forth. With some summation, very, very difficult. Okay, and then you ask, fine, so your lambda, so these calculations are fine as long as lambda is sufficiently small, but I want to know what happens when lambda is large. And holography tells you that when lambda is very large, meaning infinity, the answer is given by this.
I thought you need to take both limits, like NC to infinity.
Yes.
I mean, okay, but how can you then identify only, like, you only took one limit, no?
Okay, so both are.
I mean, because then it's like infinity.
No. Let's, yeah. I mean, NC limit doesn't play much of a role here, but yeah, strictly speaking, it takes both limits.
Well, then it's infinite. What information do I get?
Well, look, well, I mean, S is also infinite, strictly speaking, right? So S of the system which occupies infinite volume is infinite, right? But it doesn't bother you, right? Well, okay. The volume entropy density per degree of freedom, would it be more? Yeah, okay, fine. Fine. Yeah. So the n squared factor is the same in both cases. In fact, not, because if you're computing this thing as an ideal guess, remember the prefactor was n squared c minus 1, right, in front of everything, right? And here you take large n limit, and therefore you neglect this one. Yeah, thank you. Yeah, that's more correct statement. Okay. So, but I draw your attention to the fact that the entropy density doesn't really change, if you believe this answer, of course, doesn't change that much between zero coupling and infinite coupling. The change is 25%, no more. Okay, this is an interesting thing to note.
But is that result something you could check with an alternative method? Say,
No.
Young mills in the lattice,
No.
something like that?
No. Not in this theory.
So this is not something that you can. This is not a check for holography.
It's not a check.
It's a result.
It's a prediction.
Okay.
It's a prediction. Now, on the lattice, so there is a long story which I don't want to go into. Ordinarily, if you had a more sort of appropriate Lagrangian in the game, meaning like QCD, for example, right? Then, of course, yes, you go to lattice, you calculate, and you're happy, right? You obtain the similar result, for example, then it is a check. Now, this is a supersymmetric Young-Mills theory. Now, there is a long story of how people tried to put supersymmetric theories on a lattice, and let me not go into that, right? So people tried, and perhaps they're trying still. So it's not a very simple thing to do, right, for a variety of reasons. Right? But in principle, yes. If we could calculate this on a lattice, it would be a check. In fact, very non-trivial one. Fine.
Also, NC, like on a lattice, you can't use arbitrarily higher NC.
Yeah, but that is less, I think this is less problematic, because I'm aware of a sequence of calculations, for example, by Mike Tepper in Oxford, right, who actually studied the question what happens if you take NC larger and larger and larger, right? So NC equal to 7, 8, 10, and so on, right? And how your results vary with NC, right? And I think kind of the moral conclusion was they don't really that dramatically. Yeah, so perhaps this is a lesser problem. All right, so I have 15 minutes left. We are still, right, so let's compute the correlator. So we computed the thermodynamic quantity, right? But we really want the dynamical, we want to compute our viscosity and our transport coefficients. And for that, we need correlation functions. So let's compute these correlation functions. And to do that, we need a recipe. So correlators. So how can you compute correlators? Well, in general, what do you do if you need to compute correlators in quantum field theory? You have your action, and you deform your action by some term which involves some current and the operator whose correlator you want to calculate. And then you take functional derivatives with respect to J, right? And you get so the derivatives with respect to J will give you 1-point function and 2-point functions and so on, right? So this is a general kind of philosophy of what you are doing. So here it will be similar. So I will take so on the gravitational side, right? I take my background metric, which describes my state, my initial state, unperturbed state. G mu, right? And it has a gravitational action. It has a gravitational action, right, of G mu nu background, and I perturb it, right? So I take my G mu nu background plus perturbation H mu nu, right? Which means that my action will have now dependence of this type, right? Plus H mu nu. And I will, what this formula tells me is that I have to identify my generating functional on the Young-Mills side. So let me erase all of this. So I have in the limit again, so NC going to infinity, lambda going to infinity. So this is identified with e to the minus as gravitational of this particular state, which was a thermal equilibrium state described by my black brane solution. And I have this H mu nu, which will depend on the boundary conditions H naught, which I have to carefully specify. And then the recipe is the following, that this J must be identified with 1/2 of H mu with upper nu naught, right? Naught meaning the boundary value of this field H mu nu, which means, so this is the same as 1/2 of H mu nu at the boundary of my ADS space. All right. So I will not comment on appearance of this 1/2 and so on. So these are details which I can describe in private if you want, or you can read in the literature. We don't have time for this, but there is a recipe of how to. So if you want to take, so what do you need to do? So you take your background solution. It's written here. Here it is. You perturb it with your H mu nu, right, with little gravitational wave if you want. You solve equations of motion subject to some boundary conditions. You substitute this solution back into the action. You integrate by parts. On shell, the action becomes a boundary term only. And this boundary term will depend on H mu nu naught, on the boundary value of your H mu nu, which is your J, according to this formula. So all you have to do then is to take functional derivatives with respect to this object. And this is your correlator. Okay? So let's see how it works in practice. In order to see this, let me write down gravitational action here. The gravitational action will contain some prefactors. So let me write this in full glory, so at least for once, so that you sort of believed I'm not inventing this. All right, so this, there is some integral from 0 to 1 du d for x. So this is a 5-dimensional object, square root of minus g. So here you have to recognize familiar pieces, and that's supposed to make you feel more comfortable. Here you have other two pieces, minus h, bracket closed. So here kappa 10 is the 10-dimensional Newton's constant, which is related to the parameters of interest by the following formula. Now, terms which are maybe less familiar to you, so this is just a Einstein-Hilbert term in this ADS-Schwarzschild background. But there are other terms. So this term is called Gibbons-Hawking term. And a Gibbons-Hawking term is necessary to introduce whenever you have gravitational theory on a manifold with a boundary. I will not again explain why, but you may explore this subject, right? It is necessary for the variational problem to be well posed. So there is some boundary term which is there whenever you have a boundary, and we have a boundary of ADS, so we must include it. And then there is another term with yet unspecified coefficient A in front of it. So this is just a boundary volume, if you want. And this term will be necessary with A equal to minus 6 divided by L for renormalization because of course our correlation functions in principle will be divergent, right, like in quantum field theory in general, and there is a gravitational analog of renormalization procedure in quantum field theory, and we will need to add terms of this type in order to do this. Great. So now let's see how this action looks on shell. So I will write the same action when you have substituted all the ingredients, n squared c t to the fourth. So instead of kappa, I introduce these parameters. So now to bring it in the form more familiar to Young-Mills theory. And here we have -1 plus 1/2 3 h naught tt. So this capital H is just little h with one of the indices raised by the unperturbed metric. So let me not kind of explain this for a long time, because these are technical details, perhaps not very important ones. So bracket closed plus corrections of the type h squared, bracket closed. All right, so this is part of this action which will be necessary for us. And now we have to compute the one-point functions taking this action, right, according to this recipe. And the calculation tells us that, so my h mu, right, my h mu happily couples to the components of the stress energy tensor T mu. So the T00 or TTT component of my stress energy tensor at finite temperature T is given to 2, is equal to 2 variation of the gravitational action with respect to this h naught tt component, right? And you can look at the formula, and this is equal to 3/8 pi squared n squared c t to the fourth. That's the answer. And you can compute also t, for example, xx, so tzz component in a similar fashion, right? And discover that this is equal to 1/8 of pi squared n squared c t to the fourth. But these guys, so what is equilibrium? What is the value of T naught naught in equilibrium? So this is our energy density epsilon, and this is our pressure. Okay. And you can see that the equation of state emerges from this calculation that epsilon is equal to 3p. Right, so this is equation of state for this particular quantum field theory, which is superconformal. But we know that this must be the case for a theory which is conformal, because conformal theories have this interesting property that the trace of energy momentum tensor, the expectation value of the trace of energy momentum tensor, must be equal to 0. And I remind you what this T mu was. It was epsilon p p p. So if I take the trace, but I need to lower one of the indices, right? So this is T mu with upper indices, right? Mu with upper indices. I have to lower one of the indices. So this picks up the minus sign. So the trace of this thing is equal to 3p minus epsilon. And it must be equal to 0 if the theory is conformal. So this gives us equation of state. Epsilon is equal to 3p. As it should. All right? Because this calculation was exactly this only gravity calculation. And gravity calculation gave us exactly what we expected from the conformal theory. So if you want, this is one of the simple checks that, yes, we are doing something sensible. Great, but all of this was thermodynamics, but we really worry about the correlators, right? And yeah, okay. So this was one-point function from a gravitational action, right? So it's explicit. So you have a gravitational action, you just vary with respect to this thing, and you pick up the answer. Now, let's compute two-point function. And moreover, let's compute two-point function of txy, the one we so care about. So to do that, so compute txy, let's say in momentum space, omega q txy minus omega minus q retarded at finite temperature in equilibrium. So we need solution. So need solution of equations of motion, which is hxy now of diagonal component, and this is just x and y as a function of the boundary value of xy node. Right, so this is what we want to compute. And the equation of motion, how do you find the equation of motion for this component? Well, you have a system of equations of motion, r mu nu equal to the right-hand side, which I was showing on this board in the beginning of the lecture. So, and here you have a small fluctuation, background metric plus small fluctuation. So you know how to linearize the equations, and you derive equations of motion for little h from the Einstein's equations of motion, linearized with respect to little h, with respect to fluctuation, right? So equations of motion. So let me use the following notation. I will use z free for hxy. This is not an accident because it's very convenient to use the so-called gauge invariant variables, just like in cosmology, as Laura was describing in cosmology fluctuations. So this was no different. So here it's much convenient to work with gauge invariant combinations of h mu nu, right, in order to decouple our equations of motion. And equation of motion looks extremely simple. So this is z double prime with respect to u. All right, so all derivatives will be with respect to this radial coordinate u, uf, z prime, plus omega squared minus q squared f divided by u f squared z free equal to 0. So omega hat, omega bar is omega normalized by temperature, 2 pi t, and q bar is the same, divided by 2 pi t. Fine. So what we also need is the part of the gravitational action, just like here, the part of gravitational action which contains this fluctuation hxy. So we have nc squared t to the 4th divided by 8, and then limit as u going to 0, because everything is, so it's a boundary term of the action, right? You integrate by part the action, what survives is a boundary term. And the boundary term contains this combination squared, so f divided by u, z prime free, z free, all right? So, great, so we reduced the question, the problem of computing the correlator to the solution of the ordinary linear ordinary differential equation. It's something, I think. And now we have to solve the equation. There is one problem. This equation doesn't have a known solution. It's a so-called equation of the Hoyne type. The linear differential equation with 4 regular singularities. We know very well the solution with 3 regular singularities is hypergeometric equation, hypergeometric function. If you add yet another singularity, it becomes Hoyne equation, and unfortunately, we don't know the exact solution to this. But in principle, well, we can solve it numerically, yes. But remember that in our Kubo formula, we only cared about q equal to 0 in the correlator, right? So we don't need this q. And moreover, we only cared about small omega, small in comparison to temperature here. Which means that this term can be put to 0, and the rest can be treated perturbatively as a function of omega. We can solve, obviously, we can solve a linear ODE perturbatively as a function of one of the parameters, which is omega. We only need small solution for small omega. So the solution can be written immediately, perturbatively, right, for small omega. For generic omega, it's more complicated. You don't have an analytic solution. But for small omega, you can write down in one line. And the answer is the following. So you vary. So you take the solution as a function of boundary conditions, put it into the action, take 2 functional derivatives in order to get the correlator, and the answer is the following. So generically, your solution z free as a function of u, so this is not only in the small limit, but generically, it is given by, it's a second order equation, so it has two two pieces, which corresponds to the indices of this equation, 1 plus higher order terms in U. So these coefficients A and B are known as connection coefficients in ordinary differential equations. And the correlator, the expression for retarded correlator, txy from the equation is actually minus pi squared n squared c t to the fourth divided by 2. This coefficient b as a function of omega and q, and this coefficient a as a function of omega and q. So in particular, notice that so this a and b, if you knew the full solution of the differential equation, then you would know the correlator for any omega, any q, right? And or you can do it numerically. And notice in particular that, for example, zeros of this a would correspond to the poles of your correlator. So if you're only interested in the poles of the correlator, all you need to do is to solve this equation subject to boundary condition that the solution z goes to 0, because this goes to 0 automatically, goes to 0 at u going to 0 at the boundary, right? And you immediately obtain all the poles in your correlation function. But you don't need this. You only need solution for very small omega, right? And the solution, so if you solve this perturbatively, the answer is the following. It's pi squared n squared c t to the fourth divided by 8 minus I pi n squared c t cube omega divided by 8 also, plus terms of higher, right, omega squared and so on, right? So q squared. In fact, perturbatively, you can include them in q. Okay? So this is the answer. Now compare this. Compare this with the expression for the G retarded, which we had in the beginning of the lecture, and also yesterday and today in Guy's lecture. And this expression, I remind you, was pressure minus I omega shear viscosity plus higher terms in omega. So you compare, this is from gravity in the limit of infinite coupling, infinite NC, and this is Kubo, or this is from hydrodynamics and quantum field theory. So the comparison tells you that pressure P is supposed to be equal to pi squared n squared c t to the fourth divided by 8. And you can compare with our previous calculation of one-point function. It's exactly the same result. So at least there is a sanity check that we are getting what we got before. And shear viscosity, eta. Shear viscosity is pi n squared c t cube divided by 8. Again, in this limit, right? NC going to infinity and lambda going to infinity. So you remember the expression for the entropy density that we got from Bekenstein-Hawking formula. And you can also, of course, entropy, once you know pressure, you can calculate the entropy from thermodynamics immediately. So you can remember that entropy density is equal to pi squared over 2 n squared c t cube. And therefore, the ratio of shear viscosity to entropy density happens to be equal to 1 divided by 4 pi in this limit. So you can actually introduce you can reinstate the constants, and this can also be written in the following form. Okay, so this is yet another holographic result for this particular theory, for supersymmetric Young-Mills theory, in 3+1 dimensions, in the limit of infinite NC and infinite lambda. So you may wonder what happens at different values of the coupling. And so if you plot eta over s as a function of lambda, then at infinite lambda, it goes to asymptotics, which is 1 over 4 pi, so it's independent of coupling, right, which is already the interesting result. And then a correction was computed from gravity. And the correction from gravity is the following, that eta over s is 1 over 4 pi, and then 1 plus 15 zeta function of 3, some number, lambda to power minus 3/2, and then there are some corrections which have not been computed, and I don't know if ever they will be computed. But in the opposite limit, then you have almost ideal gas of your supersymmetric Young-Mills theory. So here we have asymptotics and one term. And on this side here, there is also the result. And this result is 1 over lambda squared log of lambda minus 1 with some coefficient, numerical coefficient upstairs. And this was computed in a paper by Guy and collaborators around, I think, 2006, if I'm not mistaken, right? But as Guy explained today, apart from this log, this is basically Maxwell theory, kinetic theory result, right? It's because viscosity will be proportional to mean free path or mean free time. Relativistic theory doesn't matter, and this mean free path is 1 over sigma, and sigma is lambda squared. So it's plausible, right? So this is what we know now. A log, yes. So we don't know what happens in between, right? So this is a question mark. We don't have a formula which tells us how 8 over s. So all of this, I remind you, also in the limit of NC going to infinity. So in principle, you expect corrections also in powers of 1 over NC squared. I will finish in 2 minutes. Okay, so this is what we know at the moment. Now, to finish this, let me just make several final remarks. So remark number 1 is, yeah, by the way, so we don't know this for shear viscosity, I mean how this function interpolates between the two limits, but we also don't know it for free energy in this theory, right? So free energy in some sense is much easier to calculate, but despite all this progress in integrability of this particular theory and so on, so far nobody was able to compute even the free energy. Okay, so it happens that this 8 over s equal to 1 over 4 pi result is the limit of this quantity of 8 over s for all quantum field theories with gravity dual description given by Einstein, Hilbert action. All right. So this I don't have time to talk about this more than I do now. But there is a theorem which tells you that if you have a quantum field theory, and it's known that in some parameter space, in some parameter point, it is described by gravitational degrees of freedom, even if you don't know explicitly this description, how precisely the metric and so on, it is guaranteed that this ratio must be equal to 1 over 4 pi. So there is some universality statement. It's a theorem. It can be proven. Okay. Now, of course, the corrections, so this is a limit of strong coupling, for example, here. The corrections are not supposed to be universal, right? So you have this universal limit plus some corrections which are specific for a specific theory, right? It could not be that the corrections are universal. But nonetheless, this sort of sparks some interest because this is a universality statement. Now, we have a low value of eta over s, not eta itself. Sometimes people make mistake of saying, oh, we discovered this minimal viscosity quark-gluon plasma. Right. Viscosity of quark-gluon plasma is not very different from viscosity of glass. Okay, it's a very large number. But the ratio is indeed extremely small, the ratio to entropy density. So we have low value of this parameter at strong coupling. And this seems to be a generic property at strong coupling. All right, and then the data on heavy ion collisions at RIC and LHC data suggests the values of eta over S in QCD, which we don't know, of course, right? This calculation has nothing to do with QCD, at energy level of RIC and LHC, not very far, so 1 or 2 times this h over 4 pi k Boltzmann. So there is this question of why this is so. Is it an accident? Maybe not an accident, and so on. 2 last remarks before we finish. You may wonder, so this method allows to compute actually any transport coefficients in strongly interacting theory with gravity dual. And almost all of them were computed. So you can compute, sorry, before that, so for helium-3, for example, you have this ratio is 8, roughly, it's 8 times this 4 pi k Boltzmann, etc. You can compare other liquids, including quantum liquids and so on. It's quite interesting. Now, second order coefficients, second order coefficient transport can be computed, or were computed. And coupling corrections to them were also computed. Final remark is the following, that we should not forget those non-analytic terms, which I mentioned several times. So should not forget contributions of non-analytic terms in the hydrodynamic expressions. So these are 1 or NC squared suppressed in holography, but in real life they may not be. And so this is very important topic. I refer you to a paper by Kofton, Moore, and Ramashke, where this issue was investigated in great detail with rather interesting results. And maybe a guy will talk about this, I don't know, but if not, then please read it on your own. It's about these corrections to the hydrodynamic quantities and correlation functions, which are non-analytic in frequency, and they do influence physical conclusions that you may have from these calculations. Thank you. All right, I know people are hungry and tired, but if there are some urgent questions, then yeah, please.
The dependence on the temperature and the number of colors in the gravitational action, could you remind me how you obtained that?
Yeah, so this is obtained from the fact that in front of gravitational action, there is a gravitational constant, kappa. And gravitational constant is related to, if you want, you can write this down in terms of a Planck length, right, an appropriate number of dimensions, as usual, right? So for example, in 4 dimensions, you have this g equal to L Planck squared and so on. Now, the Planck length in string theory can be related to the basic parameters such as G string, the interaction strength of strings, by comparing the appropriate amplitude. So suppose you have 2 closed strings which come together, form a loop, and go away, right? Now, the limit of this diagram in the particle limit, right, will be just 2 gravitons coming together, interacting, and so on. So you can compare these 2 diagrams, and you can relate the usual Newton's constant to the stringy parameters such as GS, right, and LS. And those are related to parameters of Young-Mills. Okay? So if you combine this together, so it's not entirely obvious from what I'm saying, but I can write this down formula for you later on, right? So this is a kind of philosophy behind this, right? So string theory relates Newton's constant in front of gravitational action to parameters LS and GS. And parameters Ls and Gs are related by duality to the parameters of dual Young-Mills theory.
Including the temperature?
No, the temperature, no. The temperature comes because of the Hawking temperature of the ground solution you are dealing with. Yeah. Yep.
So maybe I somehow missed this, but the duality you test by scattering, you said, right, on both sides, so or by kind of scattering.
Not only. So these scattering experiments of Klebanov and others were sort of heuristic arguments in order, they came before the duality.
Okay, sure.
Yeah, so this was just a motivation, if you want, before Moldasena sort of wrote this down explicitly. I mean, people in some sense knew.
So I just
that,
wonder,
yeah.
like, how do you, I mean,
how you test?
No, well, at least from what I saw, like, the
Yeah.
fields are completely different in both cases, so the field content was completely different.
Yes.
And how do you
Yes.
scatter with anything else but like a gravitational wave or graviton or whatever it is?
Yeah.
Because, I mean, there were like a mu and
Yeah, exactly. Yes. Good question. Yes. Exactly in the same fashion as, so suppose you have gravitational wave, right? And you have some theory. So for example, you have some object, for example, you have water, right? So h mu of a gravitational wave will couple to the substance in this bottle, right? Through the energy momentum tensor of water.
Yes. Yeah, but you wrote down scattering with phi, for example. How does the phi couple to this?
Phi doesn't couple to t mu. Phi couples to some scalar operator, right? Because of the indices, right? But
Lagrangian, there was no coupling to the phi of the closed string.
no, but again, so when you have the action, right? So you want to couple things to a particular theory. How do you do this, right? You write down plus j times O, right? Where j is, for example, gravitational wave, and O is the operator in your theory which couples to this particular influence, right? So of course there could be, they not always match. It may be that, for example, if you have electromagnetic wave and there is nothing charged here, right, and yeah, you cannot couple them. But
Okay,
yeah. Other questions? Yes, please.
So the reason that we don't have a dual theory to QCD, is it because the quarks are less massive?
No, thank you. Yeah, so okay, so let me say a few words about this. I'll try to be very brief, but this is an important point. Why don't we have a gravity dual to QCD, ultimately? So we want to, of course. Now, the reason for that is, roughly speaking, the following. So in QCD, what you have is asymptotic freedom, right? So this means that your coupling runs with energy scale in such a way that it becomes very small at high energy. This is QCD. Now, in theory, which we described now, it's one of the examples of dual theories, the coupling didn't run. Remember, beta function was equal to 0. So this is a super conformal theory. So in the same plot, I can draw it like this. It's a straight line, doesn't change with energy. Okay? So one may say, okay, great. So can you cook up a certain Lagrangian so that the coupling would run there and it still have a gravity dual? And maybe it's possible, right? And then you can describe QCD, for example, in this region of the coupling with a running coupling, and then starting from some scale, for example, E star, right? You still have your conformal theory. Okay, so such models exist. They can be. They were written down in the late 90s and beginning of 2000s. And then one naively can say, fine. So all I need to do, in order to describe in terms of gravity dual my QCD, I just take my scale E star further to the right. Right. In this case, I will, for example, go to this point, and then from that now on, you have conformal theory and so on. So, and in principle, naively, you can say, well, why not bringing this point all the way down to very, very high ultraviolet, right? And then I have a full description of QCD, any processes I want, except for some very highly energetic processes I don't care about. And then I have a gravity dual to a large sort of chunk of QCD. Now, this would work, except that in doing so, you lower this bar, and this means that your coupling becomes smaller and smaller and smaller, this effective coupling to which you match in the conformal coupling. And you remember our relationship between parameters like L and L Planck and L string, right? If the coupling becomes sufficiently small, it means that the geometry which you built your duality on receives large corrections from strings, from string geometry, and from quantum loops, from quantum gravity loops. In other words, once you go in this description, once you go sufficiently low, you have to consider not only gravity, but the full string theory degrees of freedom. So in principle, it's conceivable that a string theory dual to QCD exists, but nobody really knows how to build it because it's so complicated a theory that you cannot really do it in practice, right? But this rules out a gravity dual, a simple gravity dual description of QCD itself, right? You must include, because of asymptotic freedom, you must include some degrees of freedom which are stringy in nature. Okay, so that's unfortunate. All right, I think in the interest of food intake, we should close the session, so thank you all very much.